Okay, there's something called a principal ideal. It's an ideal in a commutative ring that you can write just like we wrote this thing over here, that you can actually have a fixed element and then spin everything off of that fixed element. So it turns out, if I didn't take Z on purpose, but if it turns out that every ideal that you can think of in Z turns out to be a principal ideal. Oh, it's slow. Whew. So I'm going to prove that. So I thought it would be a good idea to go back to fundamentals based off of what I saw in exam 2. Let's just start from the beginning. How do I prove something? I rewrite this as an if-then statement. So I have a know and a show that I can start tearing apart. So I'm going to write the statement, every ideal of Z is a principal ideal, as an if-then statement. If I is an ideal in Z, then I is a principal ideal. So that's how you rewrite that statement. My know is that I is an ideal. So I just copied and pasted from the previous. So what does that mean? Well, from the straight on brutal definition, that's that side. I is a subring, and I know that this condition has to hold. So subring is all the properties of a subring. And the checkability theorem gives me this additional criteria, that x minus y belongs to I for all x and y belonging to I. So I have that extra condition that I might use. So these are my puzzle pieces that I want to use. What do I have to show? I have to show I is a principal ideal. That means that I have to show that I is of this form, like that guy over there, where A is fixed. So what that tells me is, if I restate that, is there exists an A belonging to the ring such that I can express I in this form. That means that my job is very clear. I've laid it out for myself. I have to find that A. So somewhere in my proof, I have to show that A. Here it is. And so that's my goal, is to get to that point. Clear? Makes it seem easy when you have everything mapped out like this. So there's my know and show at the top. And I'm going to start strategizing now. Now that I have everything mapped out, what do I need to do? Well, I need to think about subrings of a ring. Subgroups under plus are of the form just for Z, are of this form, right? We've played around with subgroups under just plus. So if I use that idea, if I know n, I'm done, right? If I can use that and piggyback off of this, the n is the A, right? So that's where I'm headed towards. So I'm going to first throw away the 0, because if you start thinking about n times z, it's only interesting if it's not 0, right? If you took 5 times z, for example, you see that you get multiples of 5 in your 5 times z. So let me throw away 0 by itself because it's easy to deal with. If I is just 0, I'm done. I can express it this way. Nothing to do. My A is I. So assume, step 2, that I is not trivial. Then it's got to contain a positive element. How do I show that? Well, since I is non-trivial, then it contains a B that's not 0 in it, right? Because it's not trivial. Well, if B was negative, then by ideal properties, the one up here, I could take x equals 0 minus y, because it's a, right? I can just pull that in. 0 minus B must be in I by being an ideal. And because it's a subring, 0's got to be in there. So minus B is going to be positive, which is an I. So I know there's at least one positive element in my ideal. Thumbs up? Jeff, digested? I know I talk fast. Okay, so now I'm going to make a set. I'm going to take the set of x that are just positive. I claim that this has to have the smallest element. Why am I thinking in this direction? Well, I just thought 5z in my head, right? Where does the ball start rolling? 5, right? So the 5 would be my A. If I could just lock out the first positive element in there, I've got my A. So I'm after that A. So S is not empty because in step 2 I already said there's a positive element and I proved that. So there's a smallest element A belonging to I. So I told you my thoughts, that it didn't come out of the air, that I was thinking of 5z, and I was trying to capture this guy as my A and make it general. So it's not like I came out of this out of the blue or something. Thumbs up? Okay. So now I know what to do. I'm going to I know already what my I is going to be. It's going to be this thing right here because I took a few examples first and I came up with the idea and I'm headed there. So now I know my A. It's the smallest element from the positive part of I. So I formed a cyclic group generated by that smallest element A, and I claim that this is going to be a subset of I. I didn't come up with this out of the blue. I came up with this by thinking some examples, and I think some of you were thinking along this line just based off of your questions. If x is an A, then x is n times A for some n. That's the definition. But A belongs to I means y times A also belongs to I by definition of ideal, right? I'm just pulling off this definition right here. There it is. So that tells me n times A must belong to I by the definition of ideal, right? So x must also belong to I. Digest. Started with an x in here. X must be here. X must look like this. Why does x belong to I? Well, I says that any n times x must belong to I. So therefore, I'm just pulling that property down. So I've set containment. Other way around. I also is contained in A, in the cyclic group generated by A. Take an arbitrary element y that belongs to I. By the division algorithm, I can expand that guy. Y equals QA plus R, where the Q is an N, and the R must be between 0 and A. But by group properties, R is equal to Y minus Q times A, and I'm done. Now I can use the checkability condition. Y belongs to I because that's where I started, right? This guy belongs to I by step 4. I just proved that. By this condition, I have that the difference belongs to I as well. Right there. So our that should be Y. No, that's correct. R belongs to I as well. So I is contained in the cyclic group generated by A. And that's the proof. That tells me that I is of this form.
Can you go for that last part again?
Sure.
Why finding R? Why does that tell us the answer?
Because R must belong to I, and I already showed that then it has to be right of the form.
Why is it?
Am I done here? Yeah, I think I'm done.
Can you go back one more?
Yeah, because now you can express Y as...
Where do we get R from initially?
It's the remainder in the division.
We didn't get it before this?
No. It's slippery. Slippery proofs are okay.
And this only works if the integers are well ordered, right?
Right. So I was trying to avoid saying things like well ordering principles and right, but I'm using that. I need that. Okay. Any other questions?